Okay, so before we get to Weibo distribution, we I introduce everyone to exponential distribution, and I said the focus today will be on Weibo, and Weibo is a generalization of an exponential distribution. Okay, and of course, Weibo is a very good distribution for waiting time. Okay, before the occurrence of certain event. We got two parameters in the Weibo distributions. We have data and beta. The data is a scale parameter, and of course, beta is the shape of parameters. Okay. Now, this is a probabilistic representation. Okay, of a random variable x that follows Weibo distribution. Now, Weibo distribution is kind of flexible, okay, at different values of parameters. This supposed to be data, okay. Give me 1 second. This supposed to be data, okay. Well, though we have different kind of ways to present Weibo distribution, okay. So, but right now, I'm actually using the density that considered data and beta, okay, as the parameters. So when I decide to vary the parameters, I'm actually going to have different shapes, okay? And because of that flexibility, and that is what makes Weibo to be very, very useful in survival analysis, okay? And generally, time to events, okay, analysis, okay? So take a look at that. Now, in a Weibo distribution, uh, the using the probability of the Weibo, we can actually obtain the CDF. Okay, what do we mean by CDF? The CDF is actually the cumulative density function. Okay, now what I'm trying to talk about right now is that uh, if I want to obtain the CDF is an uppercase F. Okay, I want you to see the difference between the CDF and the PDF. A lowercase f is PDF, which we call probability, okay, density, okay, function, okay. But when you talk about the uppercase F, which we call CDF, okay, that is cumulative density function, okay. There's a difference between cumulative density function and probability density function. Do you know that if I'm giving probability density function of any distribution, okay, of any random variable, I can find the CDF, which is going to be probability of x less or equal to small x. Okay, that's what we mean by uh, CDF. You actually want to find the probability of a random variable x less or equal to a realized value. Okay, that's what we want to find. Now, if I want to uh, do that here now, so I'm going to do from, if you take a look at this, x greater than 0, right? I'm going to go from 0 to x, okay, because look at that, at most, okay, to x, okay, then I'm going to write the distribution. I can write the distribution, or probably I'm not going to use x again. I'm going from 0 to x, okay. Give me 1 second. So I'm going from 0 to x. So what I want to find now, I want to find this, okay, it's a CDF, which is the probability of x less or equal to small x. Okay, I want to go from 0 to x. Okay, then I'm going to use small f of probably t. Okay, dt. Look at that. So what I'm trying to talk about now, okay, for the Weibo distribution, okay, I'm actually going to have 0 to x, okay, beta divided by delta t divided by delta raised to power beta minus 1, then exponential, okay, into minus t divided by delta, okay, raised to power beta dt. So this is what I'm actually going to do. Okay, can you see that now? So when I find the antiderivative of that, okay, using the range of 0 and s, okay, and in the end, this is what I'm going to show you what we're going to get. This is what you're going to get now. Okay, can you see that? That is what you're going to get. You can try that. That is going to be your result. And that's what we call the CDF of a Weibo distribution. Okay, the CDF of a Weibo distribution. Now, what do we use this CDF to do? We actually use the CDF of a Weibo distribution to determine the probability of, if a random variable is less or equal to a realized value. Okay, so which means now if this guy here now is the probability of a big S less or equal to small x, now it means if I have that one, I can actually use it to also find the probability of s greater than x, which is just going to be 1 minus that. Okay, which is going to be 1 minus that. I can use it to find that one. Okay, which is going to be 1 minus that. Okay, and of course, if it is 1 minus that, s greater or equal to small x. Okay, so 1 minus into 1 minus the CDF that we see right now. Okay, then at the end of the day, you're going to see this is going to cancel that. Then you only go minus times minus. Then you're going to have this. You're going to have x is super that, then that. That's what you're going to have. So that is the probability of s greater than x. Okay, we use this a lot in survival analysis. Okay, what is the probability that probably some patient that undergo medical intervention, we actually we survive more than maybe 5 years or more than 7 years or stuff like that. Okay, so take a look at that. Okay, you guys confirm again, or if you guys are still hearing me clearly. Okay, thank you so much. Now that you can see this guy here is actually the CDF. Okay, now um what about if a random variable s follows a Weibo distribution? Okay, and how can we find the mean and variance? Because we may want to know, like for if a random variable x represents the numbers of time we're going to wait before the occurrence of certain events, the question is going to be, on average, how long are we going to wait? Okay, if I want to answer that on average, okay, then it means I need a mean of a Weibo distribution. Okay, there's something that we call waiting time before death. Okay, on average, how long are we going to wait? Okay, I'm talking about life expectancy right now. Okay, the mean life expectancy. If I have an electrical component, I buy an electrical component, I know I'm not going to use that forever. You know that there's going to be a time that that very component is no longer going to work anymore. So the question now is, how long am I going to wait on average? Okay, before that material is not going to work anymore. Okay, then I need a mean. So if I want to find the mean, of course, Weibo is continuous probability distribution. If I want to find the mean, of course, I'm going to use this 0 to infinity, okay, x, okay, f of x dx, okay. And what is f of x? Then you're going to use f of x of Weibo, okay, that I showed you the other time. And at the end of the day, this is what you're going to get. That is the mean. Okay. I can ask you to prove that. Okay. Using, uh, you know, the density. Okay. Using this guy here. Okay. So using the density, using this is f of x. Okay. Given this f of x, okay, you can be asked to find, to obtain the expected value of x. Okay, this is going to be from 0 to infinity, x. Then you're going to write beta divided by delta, x over delta. Okay, that raised to the power minus 1, exponential raised to the power minus x that, then raised to the power that, then the x. Okay, so when you take the expected value of x and, do what you're supposed to do, you're actually going to derive the mean of a Weibo distribution. Okay, you're going to derive the mean of a Weibo distribution. And you know what? The mean is actually it's actually right here. You can try that, okay, and see whether you're gonna get that. But if you want to get that, want to try that, you're gonna make use of gamma function, okay. If you follow what I did yesterday, use substitution method. From there, you're gonna get, find yourself where you're gonna use gamma function. Okay, if I have my time today, I will come back to this. Okay, if I have time, I'm actually gonna come back to this. Okay, there's something I want to be doing that I want to volunteer to be doing. After my class, like at 9:50 or at 9:55. Okay, I'm going to be using additional 10 minutes, and that very 10 minutes is just to walk you through some derivations. Okay, I just want to let you know. But for some of you that have lecture, you can actually opt out of the meeting. Okay. Um, And if you want to obtain the variance, of course, you know that the variance of x, okay, is expected value of x squared minus expected value of x all squared. Okay, this is the expected value of x. Now you can obtain the expected value of x squared using expected value of x squared equal integral 0 to that x squared f of x dx. Okay, where the f of x is actually going to be Weibo density. Okay, it's going to be Weibo density. Okay, now when you don't get in the expected value of x squared, you can subtract the square of the mean, then you're going to get the variance, and this is the variance. Okay, can you see that now? That's going to be the variance. So what I'm trying to show you right now, so this is the variance of Weibo. This is the variance of a random variable x that follow Weibo distribution. You can derive that as well. Okay, now let us now go into our application now. Since we know the mean and variance of Weibo distribution, I'll show you how you can actually derive that. I'm still going to, I've given you a clue on how to go about that, but you know what, I have my time. I'm going to walk you through maybe probably how to derive the mean. Okay, you guys confirm again. If you guys are still hear me clearly, can you confirm if you're still hearing me clearly? Okay, thank you so much. Now, let's go to application right now. Application is going to be easy. Okay, it's going to be easy. But you know what? If I actually give you questions under continuous probability distribution, I'm actually going to tell you the type of distribution I'm referring to. I told you the other time. Now, take a look at this. The time to failure in hours. Okay, I told you we use exponential, we use Weibo to model, the time we're going to wait until the occurrence of an event, like time to failure. Okay, the time to failure in hours of a bearing, okay, in a mechanical shaft is satisfactorily modeled by Weibo random variable with beta equal to half and delta equal to 5,000 hours. Now, to pay attention to that, if you want to use a Weibo density, you need to be you need information about the parameters. Okay, those are parameters of Weibo. Okay, you need information about them. Okay, you know why? because um, the CDF, what I call, because the CDF, the mean and the variance, they are functions of these parameters. Take a look at this. Mean is a function of two parameters, delta and beta. Okay, variance is also a function of those of the two parameters. So which means the moment you have the two parameters, you will be able to obtain the mean and variance of Weibo. Okay, you will be able to obtain the mean and variance of Weibo. Okay, so in the question right now, you've been given the values of that. Okay, the beta equal to that, and the delta equal to that, and here they ask you to find the mean. Okay, the mean time of failure. Okay, the mean time of failure. The mean time of failure is more or less like how many hours or are we going to wait, okay, before failure occur. Take a look at that. So what am I going to do? I'm applying the formula now. Here, I'm applying this formula now. I'm going to show you I'm applying this formula now. Okay, delta into gamma into 1 plus 1 over beta. That's what I want to apply right now. Okay, all what I'm just going to do is just to plug in the values of data and the beta given. Okay, now I've plugged that in now. Okay, the 5,000 right here is actually the data. Okay, and don't forget the formula have 1 divided by 1 over beta, which is that. Okay, now if you do 1 divided by day, that's going to be 2, right? Okay, and what is 2 plus 1? That's going to be 3, right? This is going to be gamma 3. Okay, and I told you yesterday, what is gamma k? Gamma k is k minus 1 factorial. Okay, you guys confirm again if you guys get that? Can you confirm if you get that? Then I want to show you. Okay, thank you so much. I want to show you how gamma 3 become 2 factorial because gamma k, according to the law, is k minus 1 factorial. And that was why gamma 3 become 2 factorial. And you know what? The 2 factorial is going to be 2. Then 2 times 5,000, you got 10,000. So what are we talking about here? Then the mean time to failure in hours of this particular item is actually 10,000 hours. I think we need to know, part of life is we don't want situation where things is going to fail suddenly. We actually want to know ahead of time. Okay? We actually want to know ahead of time. Okay, that is the essence of this. But before we can know ahead of time, we actually need a probability density function, that capture that reality, that capture that, okay, that capture the time to failure. And right now, we are assuming the Weibo distribution actually capture the time to failure. Okay, now we already know ahead that what this guy, this item is actually on average, the average time is going to fail is 10 hours. I mean, it's 10,000 hours. Take a look at that. Now, because this is just an average, okay, we also you can also if you want to tell on the how reliable is this, okay, you can go on to obtain the variance. Okay, and if you want to obtain the variance, of course, you're actually going to use the formula for the variance, which is this guy here. Okay, which is a functions of the two parameters. Or what you're just going to do just to plug in the values of those parameters. Okay, and you're going to get the variance, and so that we'll be able to know. And when you get the variance, you can find a square root of that to be able to get a standard deviation, so that we'll be able to know how reliable is the mean. Okay, and you know what? From the question, we can also answer a probability question. We can also answer, look at that. Determine the probability that a BNA lasts at least 6,000 hours. Oh my God, at least. I told you yesterday, that is a greater than sign. Okay? And when you say greater than sign, okay, I told you in the formula, the probability of X greater than a small x is 1 minus the CDF. Okay, it's 1 minus the C. Don't forget the CDF is the probability of x less or equal to that. Okay, so what are you going to do right now? You already know the CDF of Weibo, right? You're going to go into the CDF of Weibo. Okay, now you're going to subtract, you're going to say 1 minus the CDF of Weibo, and automatically, now I'm going to show you what I want to use, right now. Give me 1 second. Now, this is the CDF of Weibo. Can you see that? That is a CDF. Okay, this CDF is the probability of x less or equal to small x. Okay, the probability of at least now, that is a greater than now, is going to be 1 minus this guy, which is just going to be just this guy, the exponential is by that. Or what I'm going to do, I'm going to plug in beta, delta, and the x. Now you're going to see what we've plugged in right now. Okay, look at that. That's what we're using right here. Our x is 6,000. Okay, and we've plugged in the values of the parameters. We compute that, and the probability is actually 0.334. So what we mean, what happened is that, okay, you know what, 33.4%, okay, of all bearing will last at least 6,000 hours. Okay, that's what we mean. Okay. Okay, so we are done with Weibo. Before I go to today's lecture, is there anyone who want to ask question before I go into today's lecture? Is there anyone? Okay, like I said, I'm going to use by 9:55. I'm going to use additional 10 minutes. At least I'm going to show you how to derive the mean of a Weibo distribution. Okay, you can try how to derive the variance. Okay, but I'm going to show you how to derive the mean. Okay, I promise you that. Okay, now I'm going to stop my share now, and I want to go into today's material. Give me 1 second. Today material, we want to talk about gamma related distribution. We're still on continuous probability distribution. Okay, so today we're still on continuous probability distribution, but there's something that we call gamma related distribution. Okay, can you confirm if you guys are seeing what I'm projecting right now? Did you see that? The gamma related distribution. Okay, thank you so much. Now we have other forms of the continuous probability distribution. Okay, I could remember I started with uniform distribution. From uniform we went ahead to normal distribution, and from normal distribution we talk about Weibull exponential distribution, and from exponential distribution we talk about Weibull distribution. Right now we want to go into gamma related distributions. All of them actually fall under continuous probability distribution. Okay, I want to welcome you once again, okay, to this topic, okay, we are called gamma related distributions. Okay, now, uh, you remember yesterday I was talking about gamma function, right? We're going to use the idea of gamma function uh, in fact, you know, I want to tell you that exponential distribution, normal distribution, Weibull distribution, gamma distribution, beta distribution, they are all form of gamma related distributions. Okay, they are all form of gamma related distribution. So therefore the gamma function can be used. Okay, gamma function can be used along the line in a situation. Maybe probably you want to obtain certain characteristics of the distribution. Now what do I mean by gamma function? This is gamma function. Did you see that? So this is what we call, what I'm trying to show you right now. Okay, we have two definition of gamma alpha of a gamma function. This is what we call integral definition. Okay, this is integral definition of a gamma function. Okay, now we have integral definition. We also have non-integral definition. Okay, the non-integral definition is this. Okay, gamma alpha equal alpha minus 1 factorial. So what I have here is what we call non-integral definition of a gamma function. Okay, so, you can see what I'm trying to show you right now. We have the integral definition of gamma function, and we have non-integral definition of gamma function. Okay, now you've seen the gamma function right now. Okay, I think I've shown you now, right? Okay, So like I said, so this is a non-integral definition, okay? And this is the integral definition, okay? But you know what? Integral definition is equal to non-integral definition. So what I'm trying to talk about is that, okay, this guy here is also the same thing as alpha minus 1 factorial. That's what I mean. Integral definition equal non-integral definition. Okay, take a look at that. And you know what? Also take note of this. Okay, gamma alpha, I can write that as alpha minus 1 into gamma alpha minus 1. And if I want to continue, okay, do you know I can do? Um, give me 1 second. I can also continue to go. Um, I can write gamma alpha equal alpha into alpha minus 1, gamma alpha minus, alpha, gamma alpha minus 2. I can continue like that. Okay. Okay. Now, if that is taken, now I'm going to show you, and you have to know that 0 factorial equal to 1, right? Okay. Now, I want you to take a look at something. If y equal to x over beta, where beta is greater than 0, okay? If y equal to x over beta, okay? And for beta greater than 0, okay? Then we're going to obtain this. Then what is this? What is that? Okay? What is that? That is gamma distribution. Okay? That is what we call gamma distribution. Okay? Now, how do we come about the gamma distribution? If you take a look at the gamma function, right? Can you see gamma function? Okay? If I let y, okay? If I let y to be equal to this, okay? I'm actually going to go from gamma function, then I'm going to have what I call gamma distribution. Okay, I'm going to say that again. If I let y equal to x over beta, okay, I'm going to tell you, we're going to go from gamma function to gamma distribution. Now, what I'm trying to tell you now, we have a new distribution in place. This is gamma distribution. And I also want to prove it to you. Gamma distribution is a very good distribution for waiting time as well. Just like Weibo, just like exponential, the gamma distribution is also very, very useful probability distribution in statistics. Okay, so this is the nature. Okay, this is a probabilistic expression, okay, of gamma distribution. So the gamma distribution have two parameters, alpha and beta, okay, where our alpha is a shape parameter and beta is a scale. When I talk about shape, okay, this is a parameter that is actually define the shape of the distribution. Every probability distribution have a shape, okay? And of course, this is a parameter that is scaling that, okay? So I wanted to take a look at that. So this is what we call gamma distribution of two parameters. Okay, do you know that every probability distribution have a CDF? I think I showed you the CDF of the CDF of Weibo the other time. Okay, if the CDF of gamma can also be derived. Okay, but only that the CDF of gamma is not tractable. Okay, it's we're actually going to have what I call incomplete gamma function. Okay, now take a look at that. The probability of, for instance, if I want to get a CDF, okay, if I can get the probability of that greater than that, all I'm going to do is to subtract that from 1, and that's going to give me the CDF. So if I first obtain this for gamma, okay, where I'm going to, so I can have something like this. Okay, did you see that now? So what I'm trying to talk about, in essence, is that we can obtain the CDF of gamma, go all and long, to have what I have it. Now, because of what I want to do now, I'm going to stop the share, I'm going to walk you through something now. I'm going to obtain the CDF of gamma distribution, okay, of this distribution. And not only that, I'm also going to obtain the mean. Okay, this is a moment generating function. Then I'm going this is the mean, it's alpha beta, the variance is alpha beta squared. Okay, and I will quickly do that for you. Okay, so give me 1 second. I'm going to stop my share and I'm going to do that for you. Now, I'm going to share my whiteboard right now. Okay, when x follows gamma, okay, with parameter alpha, beta, okay, f of x, okay, equal um 1 over gamma alpha, okay. Um, let me see. I think I have um give me 1 second. Actually going to write the density out so that I can derive the mean and variance for that. Okay, so beta raised to power alpha, x raised to power alpha minus 1, exponential raised to power this. Okay, this is the gamma, right? That is gamma distribution. Okay, so you can see that. That is gamma distribution. Now, if I want to obtain the um, the CDF, I'm gonna do f of x equal. Okay, don't forget x is greater than 0, right? Then I'm gonna do 0 to x. Okay, f of t dt. Okay, so this is the same thing as finding the probability of x less or equal to that. Okay, I want to get the CDF. Okay, like I said, you can actually take the picture, you can write. Okay, you guys confirm again if you guys are still hearing me clearly. You still hearing me? Okay, thank you so much. If you are following what I'm doing, right now I want to obtain the CDF of a gamma distribution, and I also want to obtain the mean, okay, of a gamma distribution. But right now, I want to obtain the CDF, okay, of a gamma distribution. Okay, if you understand what I'm doing up to this junction, I need you to comment yes or you say yes. Okay, thank you so much. Now, I'm going to write 0 to x, okay, 1 over gamma alpha, okay, beta raised to power alpha, t raised to power alpha minus 1, exponential raised to power t, that then dt. Okay, that's what I'm going to have right now. Okay, now if I have that one, okay, I need more room. Okay, so what I want to obtain is the CDF. Okay, like I said, I want to obtain the CDF. Okay, so I'm going to write f of x equal 1 over gamma alpha beta raised to power alpha, okay, is 0 to x, okay, t raised to power alpha minus 1, exponential raised to power minus t over beta dt. This is what I'm having right now, right? That's what I'm having right now. But that's where we are right now. Okay? Now, that is where we are now. Okay? If you take a look at my exponential, what is my exponential? What is the exponent? Exponential is carrying negative t divided by b. I'm talking about this guy here. Okay? I needed a new variable. So I say, okay, let y be equal to t over beta, right? Okay, don't forget this implies that t, give me 1 second. This implies that t equal to beta y, right? Okay, now what is the y dt? Because I'm no longer going to use the t. Okay, what is the y dt? That is 1 over beta, and that also implies that my dt is actually beta dy. Okay, my dt equal beta dy. So if I want to write that now, I'm going to write f of x equal 1 over gamma alpha beta raised to power alpha, okay, is 0 to x. Okay, now instead of t, I'm going to write beta y raised to power alpha minus 1, then exponential raised to power minus y. Instead of the t, I'm going to write beta dy. Okay, if you are following what I'm doing up to this junction, okay, I need you to say yes or you comment yes. But if you don't understand, please ask question now. If you don't understand, please ask question now. I'm going to explain that to you. Oh my God, thank you so much. They are getting it. Okay, now I'm going to clean up. I'm going to clean up. Okay, so when I clean up right now, okay, when I clean up right now, I got f of x, okay, equal 1 over gamma alpha or beta raised to power that is 0 to x beta raised to power alpha minus 1, y raised to power alpha y minus 1, exponential raised to power that beta the y. Okay, now you're going to see that this guy here, okay, if you combine this and this one, okay, that's going to give you b raised to power alpha, right? And that is going to cancel, that's going to cancel, right? Okay, and when that cancel, I'm going to have 1 over gamma alpha 0 to x y raised to power alpha minus 1 exponential raised to power that the y. Now look at what I got now. Okay, now if you take a look at what we did yesterday and what I just showed you today about gamma function, okay, you know, when let's if the upper one is infinity, can somebody tell me what I'm gonna get? Like, take a look at this guy here. You know that gamma alpha, okay, from the integral divination is 0 to infinity this exponential raised to power this is the y. Okay, I think you know that that is gamma alpha, right? Okay, now but this time around, this is not infinity, this is x. Okay, that is not infinity, that is x. Okay, so therefore we call that incomplete gamma function. I'm going to say that again. We call that an incomplete gamma function. Okay, we call that an incomplete gamma function. Okay, so what I'm trying to tell you now, this is the CDF of a gamma distribution, because it can incomplete gamma function, it terminates at a particular values of x. Take a look at that. Okay, now if you use the entire range, okay, I'm going to tell you something now. Like for instance, if x is infinity, okay, if x is infinity, what are you going to have? Okay, you're going to be 0 to infinity, right? Y raised to power alpha minus 1. You're going to have this guy here, and this guy here is what? That is gamma alpha. Okay, so gamma alpha, the whole of that is gamma alpha, and that's going to give you 1. Okay, which confirm that the CDF, when it terminates at infinity, when you consider it up to infinity, okay, which means you are using the entire range from 0 to infinity, is actually going to give you 1, which is the total area under a curve. The total area under a curve is actually going to be 1. Okay, it's actually going to be 1. Okay, so I think I just walk you through the CDF now, right? Just know the CDF now. Now, how can we find the mean? Okay, how can we obtain the mean when you have a gamma distribution? Okay, how are we going to obtain the mean? Okay, I'm going to show you right now. Okay, I'm going to show you right now. Okay, you have x follows gamma with parameter alpha and beta, where f of x equal 1 over um, um, beta raised to power alpha gamma alpha x raised to power alpha minus 1 exponential raised to power minus x over that raised to power that. Okay, if you take a look at the gamma distribution that we wrote the other time, okay, I think this is missing. Okay, now if you look at that, that is our gamma distribution, right? Now the question now is, how can we want to show that the mean, okay, the mean of gamma is alpha beta. Okay, we want to show that the mean is that we want to show that the variance of x is alpha beta squared. We want to derive that. Okay, so how can we show that the mean of x, the expected value of x, is going to be alpha beta, and the variance of x is going to be alpha beta squared? That's what I want to show you right now. Oh, can you guys confirm again if you are still following me? Are you guys still following me? Okay, thank you so much. Now, I want to use the method of movement. I can use the method of movement. I can use the method of movement generating function. Okay, but let me, if I want to use the method of movement, okay, I'm going to have expected value of x equal 0 to infinity. Don't forget that x is greater than 0. Okay, so 0 to infinity x, then the function now 1 over that, which is gamma, okay, x raised to the power this, exponential raised to the power that, dx. I want to find the mean, okay? I want to obtain the mean of a random variable x that follow gamma distribution. Okay, so I'm going to bring out the constant, okay? Then I'm going to have 0 to infinity x. You know, when I combine this guy and this guy, right? That's going to be x raised to the power alpha. Okay, then exponential raised to the power minus x dot dx. Can you see where we are now? Okay, that's where we are now. Okay, the next thing that we're going to do now, okay, since that is where we are, I need more room. Okay, I'm actually going to clean this guy now. I'm going to clean this guy now. Okay, you know where we are now, right? Okay, you know where we are. Okay, now the expected value of x, okay, equal. Okay, I'm going to let I can let y be equal to give me 1 second. Um, you know, based on what I have now, I can let y to be equal to x over beta, right? And that implies x equal to beta y, okay? And what is the y ds? The y ds is 1 over beta, and that implies ds equal to beta dy, okay? I'm actually going to plug that in now. So expected value of x equal 1 over beta raised to power alpha, gamma alpha, 0 to infinity. Now, instead of x raised to power alpha, okay, I'm going to write beta y raised to power alpha, okay, exponential. Instead of that, I'm going to write raised to power minus y, and instead of ds, I'm going to write beta dy. Okay, if you understand it up to this junction, I need you to say yes or you comment yes. If you understand what I've just done up to this junction, I need to say yes or you comment yes. Okay. If you don't understand, can you ask me question? If you don't understand, please ask me question. If you don't understand, okay. Now that's where we are now. Okay, all what we want to do now, just want to simplify. Okay, how do we simplify? Okay, now this is going to be this gamma alpha 0 to infinity beta raised to power alpha here, and if you combine that, okay, plus 1, okay, then you have y raised to power alpha exponential there the y, okay, and you know if you look at this guy and this guy, okay, you're actually going to have beta divided by gamma alpha, okay, from 0 to infinity y raised to power alpha exponential raised to power that the y, okay, so that's what you're going to have. That's going to cancel that. Okay, so I need more room. I need more room. Okay, now I'm going to write expected value of x. Okay, equal, or give me 1 second. Um, yep, I'm going to write expected value of x equal beta, okay, divided by gamma alpha. Then from 0 to infinity, y raised to power alpha exponential raised to power this y. Can somebody tell me for extra credits, okay, what I have in the parentheses? Okay, if you want to use the idea of gamma function, what is that? Can somebody tell me what gamma is that? If you want to use the idea of gamma function, what I have in the parentheses, can somebody tell me what is it going to be?
Gamma alpha minus 1.
Are you sure? You want
Uh,
to try?
plus 1.
Is that what?
Alpha plus 1.
Oh, gamma alpha plus 1. Look at me. You doing that is good job. That's gamma alpha plus 1. Send me an message for extra credit. Good job. So it's going to be um this is going to be gamma alpha plus 1. Okay, what I have in the parentheses. Okay, we're using the idea of gamma function now. And you know what? Uh, Gamma alpha plus 1 is the same thing as alpha gamma alpha. I think you know that. This guy here divided by gamma alpha. Oh my God. What do I have now? I've already shown that the expected value of x is alpha beta. Did you guys see that? That is how to show that. Okay. Now you can do the same if you want to find the expected value of x squared. Then you can find the variance. Okay. Okay. If you understand what I've done right now, Okay, if you understand this derivation, uh, I need you to comment yes or you say yes if you understand all what I've done. Oh my God, somebody said pretty much. Good job. Thank you. Okay, now it is the time. I told you I was going to show you, I promise you on Weibo when it is 9:50. Okay, give me 1 second. I'm going to stop my share right now. Okay. I told you I'm going to be taking things slowly. Okay. I wanted to understand everything. So that's why I'm just, taking things slowly. Okay. I'm going to project my screen for Weibo. Uh, okay. Give me 1 second. I'm actually going to do something right now. Um, I want to see whether you guys are seeing my whiteboard. Let me see. Can you guys see my whiteboard? Can you confirm that? If you see my whiteboard, can you confirm? Oh, okay. You see my whiteboard, right? Okay. The other time, um, you know, when X follows, Weibo, okay, Weibo distribution with parameter data and beta. Okay, we have f of x equal beta divided by data and x over data raised to power beta minus 1 and exponential raised to power minus x over that and everything raised to power that. Okay, now I want to show you how, I want to show you how you can actually obtain the mean. Okay. Now, if I want to obtain the mean, I'm going to say expected value of x, okay, integral 0 to infinity x. Then I'm going to write Weibull density. Okay, I'm going to write Weibull density. Okay, take a look at that. I'm going to write Weibull density. Okay, the x. Okay, you see that now? Okay, so if that is what I have, let me simplify. Okay, if I simplify, okay, I think I have a constant, right? So maybe beta, okay, divided by, let me see, I have a data here, I have another data raised to power minus 1, then it means I'm going to have that, right? Okay, then it's 0 to infinity. When I combine this guy and x raised to power beta minus 1, I think I'm going to have x raised to power beta, okay? I'm going to have x raised to power beta, right? Then exponential raised to power minus x over that raised to power beta dx. Now, is there anyone who understands it to this junction? Is there anyone? My 10 minutes start from now. This is 9:55. And for those of you that have lectures, you can actually opt out of the meeting, okay? Because this is being recorded. Okay, so if you understand it up to this junction, I need you to comment yes or you say yes. If you understand it up to this junction. Okay, thank you so much. Now I need more room. Okay, I need more room. Okay, I need more room right now. Okay, I need more room. Okay, need more room. Okay, so I'm gonna write expected value of x. Okay, so what we have right now is just this guy. Okay, is 0 to infinity. X raised to power beta exponential raised to power minus x over data. Okay, raised to power beta. Okay, dx. Okay, that's what we have right now. Okay, so what are we going to do? We're going to use substitution method again. Okay, we're going to write let y, okay, be equal. Exponential is carrying a lot of stuff, but I want exponential to carry a single variable. So I'm going to write y equal to this. Okay, I'm going to write y equal to that. Don't forget, so it's going to be like x raised to power that and that raised to power that. I think you know that. Okay, and this implies, what does that implies? It implies x raised to power beta equal to what? Equal to y data raised to power beta. You know that? So that if here, I'm actually going to plug in that. Okay, and you know what? I can no longer do antiderivative with respect to x. Then I need the y ds. Okay, I need the y ds. Okay, my dy dx is actually going to be beta or x raised to power beta minus 1 divided by that. Okay, and if that is what I have, so what is going to be my ds? Okay, so my ds is going to be delta raised to power delta dy divided by beta x raised to power beta minus 1. Okay, so take a look at that. You see that now? So, and I'm actually going to make some substitution right now. Okay, now, if that is what I have, we know that if x beta, there's something I want you to see right here. Okay, there's something I wanted to see. Okay, let me just create a space. Okay, x is the same thing as y raised to power 1 over that. Okay, um, you know, and data. I tell you know that. Okay, if you want to find x, if x raised to power beta equal to that, okay, it's gonna be that, right? So my x equal to that. Okay, I tell you see that now. So if my x equal to that, so what I'm gonna do now, I want to start substituting. Okay, let's first substitute for x raised to power beta. Okay, if you want to substitute for x raised to power beta, it's gonna be y data raised to power that. Okay, I'm using this guy now, right? And that is going to be exponential raised to power minus y. Okay, and what is going to be ds? Oh my god, ds is actually right here, right? Okay, so going to write data raised to power beta dy. Oh, give me 1 second. uh dy, okay, divided by beta x raised to power beta minus 1. Okay, now, but I'm going to plug in, I already know my x. Give me 1 second. I'm going to clean up. Okay, I'm not going to clean x because I'm going to substitute for x. Okay, now, the way it is now, I'm going to substitute for x. But before substituting, I can first do this. This cancel that, right? Okay, so right now I got beta 0 to infinity exponential um raised to power minus y. Okay, um y exponential square minus y data raised to power that. Okay, the y divided by now beta. Okay, now instead of x, I'm going to write y raised to power that data everything raised to power beta minus 1. Okay, I'm plugging in x. Look at that. I told you before. Okay, now I need to simplify. Now I need room. Now I need to simplify this one now. So let's do algebra now. Okay, this guy is going to cancel that guy, right? Okay. Now, when you continue the simplification, if I brought out data raised to power beta, okay, 0 to infinity, y exponential raised to power this, the y, okay, divided. Don't forget we have y, okay, raised to power 1 over beta. That is going to be raised to power beta minus 1. Okay, and we now have data raised to power beta minus 1. Take a look at that. Okay, now if that is what you have right now, okay, we can simplify more. If you simplify more, this is going to cancel that, and data raised to power minus 1, we're going to go up, we're going to become data until you know that. And when it become data, then I'm going to have 0 to infinity. Okay, now I want to combine, I want to simplify this. Give me 1 second. You know, I got y exponential raised to power minus y, the y divided by, if I simplify this, I'm actually going to have y. That's going to be 1 over beta times beta. That's going to be 1 minus 1 over beta, right? I'm simplifying that, right? Okay. Now I'm going to combine this and this because that guy is going to go up. Okay. It's going to go up. Okay. When it go up, we're going to see something right now. I think it's becoming more interesting. It's becoming more interesting. Okay. Now I'm going to write this now. Okay. I'm going to write expected value of x. Okay. Equal or data or 0 to infinity. Okay. Now, if that guy go up, you're not going to have y and another y 1 over beta minus 1. Look at that. 1 over beta minus 1, then exponential raised to power minus y, the y. Oh, combine this guy. Combine that guy, 0 to infinity, y, raised to power that. Look at that. You combine that, then this, the y. Can somebody tell me, using the gamma function, what is that going to give? The one in the parentheses. Can somebody tell me? Using the gamma function, what is it
Mm,
going to be?
Gamma 1 minus gamma gamma 1 over beta plus 1.
Okay, I think I think somebody give the correct one in the chat. I'm going to check the chat. I think somebody said, give me 1 second. Let me check my chat. Oh, somebody said gamma 1 over 1 plus k. Why did you say k? You are very close.
I meant beta instead of K.
Oh, you mean
So
beta, right?
yeah.
Okay, you got it right. Look at me. Good job. Okay, good job. Send a message to me for extra credit. So you're going to have this. It's going to be gamma 1 plus 1 over that. Okay, so which is the mean? Okay, we succeeded in showing the mean. Okay, let me write it very well. So, we've got expected value of x, data. Okay, gamma 1 plus 1 over beta. Okay, this is the mean. Okay, good job. Okay, so like I said, actually promised I was always going to be taking things slowly, walking you through derivation because I really want you to understand theoretical statistics. If you look at the course is theory of statistics, and you need to know how some models, some distributions have been derived. Okay, so I'm going to continue from here on Monday. Is there anyone want to ask question before I go today? Is there anyone want to ask question before I go today? I want to appreciate everyone for attending my lecture today. I'm going to commence my office hour immediately. Okay, after I opt out of the Zoom meeting right now. I'll make sure you guys stay safe and have a good day, guys. Okay, bye for now, guys. Okay, you're welcome. Thank you too. Thank you too.